Good afternoon, everybody. My name is Mustafa Mohammed, and I'll be talking about structural steel connection design today. I am a structural engineer, and I'm a faculty member of the University of Illinois at Chicago. And structural steel and steel connections is one of my areas. Whether it's at the academic level or at the practice level. Please, during the presentation, you can ask your questions, the chat or the Q&A, and I'll be glad to answer them. Okay, and steel, connection design is just like any other design, is controlled by limit states. The main issue here is that in connection design we have many possible limit states, and that depends on the connection type, whether it's a bolted connection, or whether it's a welded connection, whether it's a steel to steel or a steel to concrete. So, and of course, it depends on the load that's applied to the connection and the connection configuration. So this slide shows a summary of all possible limit states that you may see in a connection design, and we will cover most of these limit states, the provisions of how to find the capacity for a limit state, for angles, for plates, for bolts, for welds, etc. And then we'll talk about the specific type of connections, like the most commonly used ones. Okay, the references are the 360 AISC 360 2016 chapter J. That's the connection chapter in AISC, and it's the largest chapter in the specification. And then AISC manual part 7, which is the bolts, and part 8 with the welds, and design of connections, which are parts 9 through 13 of the AISC manual. So as you can see, chapter from part 7 to 13, that's related to connection design specifically. In addition to chapter J, which is in the specification in part 16 of the manual. The most commonly used type of connections are of course, the shear connections. And among the shear connections, the most commonly used ones are the double angle connection and single plate connection, or as known the shear tab connection, shear end plate connection, and stiffened connection, and single angle connection, and T-shear connection. We'll be talking about these, and also we'll talk about moment connections and the design of moment connections, which is covered under the same limit states that we will discuss. For bolts, the most commonly used bolts are listed in the AISC manual in the 15th edition. So we have the A307, which are called the machine bolts. These are older types that are still used, these days, but not for, connecting structural members to structural members, rather connecting components to structural members. And then we have Group A, which is high strength bolts, such as A325 bolts, and we have Group B, which is also high strength bolts, such as A490 bolts. These are the two common ASTM specifications for bolts, but there are other that are shown at the bottom of the slide. We have Group A bolts, we have F1852, A354, grade BC, and A449. And the same thing for Group B. We have several ASTM specifications for those. Typically, we would use A325 for typical applications, normal applications. Sometimes we have to use A490 if we need higher strength and less number of bolts. And that, of course, depends on the loads and the connection configuration. But we would start with A325 typically. And when we specify the bolts, we have to specify the type, whether it's N, X, or SC. N and X are related to bearing type connections, and these are, most commonly used ones, where there's a bearing between the bolt and the bolt hole. So N is when the threads are included in the shear plane, and X is when the threads are excluded from the shear plane. Now, of course, the capacity is different between N and X. So when they are included, then we typically would have less area, so the capacity would be less. If it's X, then we'll have the full solid shank of the bolt, and the capacity would be higher. So typically in practice, we don't know how this is going to be installed and where the threads would be. So practically, we would use the N type, which is the one with capacity. We guarantee if it comes to be X, then we have more capacity, but if it's not, we have accounted for that in our design. And then we have slip critical, which is used in applications, and when we long slotted holes, and when the load is parallel to the long slotted side, and that's used for specific applications. And here the capacity would depend mainly on the friction between the connected steel members. Now, the bolt limit state. So in general, when we have bolted connection, we have many limit states that we have to check. If it's a welded connection, we have much less limit states that need to be checked. But on the other hand, welding is it's advised to use bolts first as a first option because it's easier and it's cheaper rather than welding. But if we cannot do that, then we have to do welding. Welding is more expensive, and sometimes it's hard to perform in the field, depending on the connection configuration and the location and how the welding will be executed in the field, such as overhead weld. Now, the nominal strength of the fasteners is given in table J3.2. And here we have different types of the fasteners. We have A307 bolts, Group A, and Group A when the threads are not excluded, and Group A when the threads are excluded, and Group B is the same thing. We have the nominal tensile strength, and we have the nominal shear strength and bearing type connections. That's FNT and FNV, respectively, for each type. So that's the nominal shear strength given to us in KSI or megapascal if we are using metric. And of course, to get the capacity in kips, this should be multiplied by the bolt area. So that whether it's included or excluded, and whether the threads are included or excluded in the shear plane, this is accounted for, as you can see in the table. So for example, for the shear, if NV Group A bolts, when the threads are not excluded, we have 54 KSI. And Group A, when the threads are excluded from the shear plane, we have higher capacity. So the threads are excluded, they are not in the shear plane, so we have higher capacity. Okay. So that's for this. And then we have the available shear strength of the bolt is given in part 7. We talked about part 7 as being for the bolts. So table 7.1 gives us the available shear strength of the bolts. So again, we have group A, group B, and then the group C, which is introduced to the 15th edition of the AISC manual. And whether the threads are, thread condition, whether they are included or excluded. And then we have F and V over omega, that's in F and B and ASD. And then phi, F and V and LRFD, that's in KSI. These values, when multiplied by the area, we will get the capacities on the right for each bolt diameter. So 5/8 of an inch, 3/4 of an inch, 7/8 of an inch, 1 inch, and then in the same table, in the lower part of the page, you have higher diameters that are used. So here you have the capacity, so that's small Rn over omega and phi Rn. So these are the capacities for one bolt in shear. And then we have the loading condition. So we have S, that's for single shear, and D for double shear. So for example, if we have a double angle connection to a beam web, so here we have one angle from each side of the web, so we have double shear, so the capacity is higher. As you can see, for 3/4 bolt of if you put 3/4 inch bolt, we have in LRFD 35.8 kips. If we have a single plate connecting to the web, that's a single shear, that's 17.9. And then also we have table 7.3, that's the slip critical connection, which depends on the slip resistance. So we have, for class A fairing surface with mu equals 0.3. Here we have the capacities, again, depends on the hole type, whether it's a standard hole or a short-slotted hole or oversized hole, etc. And whether we have a single shear plane for S and double shear plane for D, and then for the different diameters. Bolt bearing, that's another limit state for a bolted connection. So when there's a bearing between the bolts and the bolt holes, as you can see in the figure, if yield is reached, then we'll start having, plastic, we'll get into the inelastic range, the plastic range, and we'll have inelastic deformation and permanent deformation at the bolt holes, as you can see in the figure. Now, this is calculated in different ways depending on the conditions that we have. And of course, the type of failure also varies. So we have two types of failure that are possible, and they depend on the distance between the bolt holes and the distance from the exterior bolt at the edge at the top to the end of the member. So that distance is important. So meaning that it depends on the spacing between the bolts or the bolt holes and depends on the edge distance. So the first case is when we have a tear out. So a tear out is when part of the steel is, completely removed as a result of, bolt bearing. And the capacity for that is given in the equation shown, 1.2 times F sub U times L sub C times T. And whether we're using LRFD or ASD, they are shown. Now, T is the material thickness. F sub U is the ultimate stress, and that's for the material, for the plate or for the beam web, or for the brace, for the steel material itself. So if it's A36 steel, that would be 58 KSI. If it's A992 steel, that would be 65 KSI. And T is the thickness of the material, and L sub C is the clear edge distance measured from the edge of the hole to the edge of the material or the next hole. So it's either the clear distance between the holes or the clear distance from the edge of the hole to the edge of the material. And then we have bolt bearing. And bolt bearing, that is the other possibility. When we don't have a tear out, we just have bearing failure, similar to what's shown in the figure here, where we have plastic deformation developed around the bolt holes, and that's calculated using the equation shown. And that's we call this bearing failure. That's 2.4 times the diameter of the bolt times the thickness of the material times the ultimate strength of the material, F sub U. And again, whether it's LRFD or AISD, we use the appropriate factor. Now, in general, if the clear distance exceeds 2 times the diameter, bearing on the connected material will be controlling the design. So if we have to avoid, typically to avoid tear out failure, we'll increase the spacing between the bolt holes. Now for this also, there is a table where we can get values from of these equations from the AISC manual from part 7. So there's a table 7.4, that's the available bearing and tear out strength for bolt holes based on bolt spacing. So this is based on bolt spacing. So going back to the figure here, so in a connection like this, we have bearing between the bolt holes here. That's bolt bearing based on bolt spacing, and then we have bearing also from the edge bolts to the end of the member, to the edge of the member here. So we have 2 types, and they should be added together. So this is one between depending on the bolt spacing, and then we have the other. So we have to calculate each separately and add them together. So here, if you notice, the units are in kip per inch. And of course, this is made because we don't know what material thickness we are dealing with. And typically it will, usually if we have an issue with bolt bearing, we look at the thickness of the plate, and we may increase that to, solve this issue. So we get the values from the table that's in kip per inch, and then multiply that by the thickness of the material to get it in kips for the tear out strength that depends on bolt spacing. Okay. Again, the values here are given for a small rn, that's per 1 bolt. So if we have, for example, 2 bolts, like the figure here for the tear out case, then we multiply the capacity by 2. If we have more than that, 3, 4, we multiply it by that number. And again, F sub U depends on the material that we are dealing with. So if it's A36 steel, F sub U is 58 KSI, and if it's A992 steel, we have 65 KSI. So these are the most commonly used material here. That's why they are listed in the table. Now, table 7.5 is the available bearing strength and tear out strength that's based on the edge distance. Okay, so going back to the figure, so this is for the top part, and this depends on the edge distance. Okay, so bolt spacing depends on, for table 7.4, so that we take that value multiplied by 2, that depends on this. And then from table 7.5, we take the capacity for 1 bolt, we multiply it by 2, we add it to the value we got from table 7.4, and that will be the bolt bearing capacity of the connection. Okay, so this is exactly the same thing. Here we have one thing, which is the edge distance, L sub E. So here we are given, the table is built is on two values, common values, 1¼ inch or 2 inches. If you have something different, you can use the equation, of course, to calculate that. These tables are based on the equations that we discussed earlier. And here we have, a snapshot from the AISC manual for the bearing and the tear out equations. And here we have, for example, we talked about the first equation with J3-6A. And this equation is used when deformation at the bolt hole at service load is a design consideration. So if the deformation is a design consideration as a bolt hole, we use this. But if the deformation is not a design consideration, we have higher capacity. We can get higher capacity. So Rn will be 3.0 times D times T times F sub U. And the same thing for the tear out. So the 1.2 equation depends on when the deformation is a design consideration, and then the 1.5 is when it's not a design consideration. Bolt, and under bolt limit states we have bolt tension also. So again, depends on the load how the load is applied to the connection. So here we have the same equation that we discussed before. It's F sub n times the area of the bolt. But in F sub n now, we use F sub nt from table J32, that 3.2 that we discussed earlier. So there's FNT and FNV in the table. So if it's bolt tension, we use FNT, and AB is the bolt area. Now table 7.2 in the AISC manual gives the available tensile strength for bolts. And again, for different groups A, B, C, and A307, we're given the tension stress in KSI, and we're given the capacity in kips for the different bolt diameters, and that's again for a single bolt in small rn, in ASD and LRD. Block shear, that's another bolt limit state. So block shear is a combination of shear failure and the tension failure, as you can see in the figure. So it's a block. It's a failure of a block of steel. This is if the load, for example, this is a shear failure. The shear failure if the load is from left to right in the figure here, and then its tension, and then the tension is in the perpendicular direction between the two rows of bolts. So we have a combination, if the load is from left to right, so we have a combination of shear failure and the tension failure. So the shear rupture equation has the shear rupture term, which is 0.6 times F sub U times ANV, and that's the net shear area. And then we have also the tension part, which is UBS F sub U times ANT. F sub U is the ultimate strength of the material, and then ANT is the net tension area at the location of the bolts here, and this has to be compared with the yield, the yield shear strength, which is 0.6 F sub Y times the gross shear area AGV plus UBS times F sub U times the ANT. That's the tension component. Now UBS is a factor, and it's equal to 1 when we have a uniform tension stress distribution. So it's equal distribution at the tension part, and we use 0.5 if it's non-uniform tension stress. So typically on braced connections and hanger connections, when we have an axial load applied, we will have UPS equals to 1. But in shear connection, for example, in shear connection in coped beams, we will have, especially when we have multiple rows of bolts, we will have non-uniform tension, so we'll have 0.5. So the two sides of the equation should be, checked, and the smaller one will control. Now, instead of using the equation, we can use these terms, the different parts here, 0.6 F sub U A and V, or F sub U times A and T, or F 0.6 Fy times A G V. Those three parts are given in tables here. So this is in part 9 of the manual. So we have a block shear tension rupture component. Again, this is in kip per inch because it's applicable to any thickness. So here you have the terms F sub U times A and T divided by T. So we can you just need to multiply by the thickness that you have, divide by omega, or in L of D, phi F sub U A and T divided by T. And that's for different bolt diameters. So this is for 7/8 of an inch. And this is block shear yielding component. So that's 0.6 Fy times A sub GV, the same thing. Yeah, we have for different material, 36 KSI and 50 KSI yield. And this is the shear rupture component, F sub U, A, and V. Now the minimum spacing and edge distances. So this is given in section J3.3. The minimum spacing is 2 2/3 times the diameter. The preferred is 3 times the diameter, and the edge distance is S/2. D is the nominal diameter of the bolt. Commonly used S is 3 inches and E is 1.5 inches. Of course, this is typically for bolt diameters that are 1 inch or less. Okay, for the weld limit states, so now for the most commonly used type of weld is the fillet weld, and that's given in equation J2-3, where we have FNW times AWE. FNW is the nominal stress of the weld metal per unit area, and that's equal to 0.6 times FEXX, which depends on the electrode that's used. And AW is the effective weld area. So for fillet weld, we have 0.707 times the weld size. W is the weld size times the length of the weld. And also one thing that need to be checked is the nominal stress of the base metal. So that has to be checked along the weld line as well. Okay, now for a linear weld group loaded through the center of gravity, the capacity can be calculated using equation 2-4, which is FNW times the effective weld area, and FW is 0.6 times FEXX times, in parentheses, 1 plus 0.5 sine theta to the power 1.5. That's equation J2-5. Now, of course, as you can see from the equation, if the theta is the angle between the load and the weld line, between the applied load and the weld line. So if the applied load and the weld line are parallel, theta is 0, sine theta is 0, so we'll have 0.6 times FEXX. But if you have an angle, then we will have higher capacity. And if it's, for example, 90 degrees, then you'll have 1.5, the parallel capacity. So we can take advantage of that if the load is applied at an angle to the weld line. Now for weld group that is concentrically loaded and oriented longitudinally and transversely, the capacity of the weld group can be calculated using the greater of equation J2-10A or J2-10B, where we have RWL, that's the nominal strength for the longitudinally loaded weld without considering angle of the load, and then RWT, that's the nominal strength of the transversely loaded weld without considering the angle. So that's one way to calculate it. And then you have the other one, which is 85% of the longitudinally loaded weld plus 1.5 times the transversely loaded weld, and then the greater from the two. Now, we looked at the bolt-related limit states and then the fillet weld limit state. So these are applicable to the connections that we use. Now there are limit states related to the connecting elements, the plates that connect, two members, together, or angles or channels, connecting elements, in general. So we have the tension yielding that's given in equation J4-1. That's Fy times Ag. And we have the tension rupture, that's F sub U times the effective area. Now, as you can see here, and maybe also in the block equations, whenever we have yielding, we use the yield strength and the gross area, always. So if it's yielding, we use yield strength and gross area. If it's rupture, we use ultimate strength and net area. Okay, if it's rupture, we use ultimate strength and net area. So here we have tension rupture is F sub U times AE. AE is the net effective area. Okay. And then, so the shear yielding, so here we have tension yielding and tension rupture. So you can see how this happens, in the figure. So we check both. So for tension yielding, we don't consider the holes. So we just take the whole length. That's the gross area. The whole length times the thickness. If it's tension rupture, we have to subtract the whole diameters times the thickness. Shear yielding, same thing. Now shear yielding, as you can see, that we use yield and gross, yield strength and gross area. So yielding will occur in the gross areas, as you can see. Rupture will occur along the net area. So we have to check that, and then we have to check shear rupture, 0.6 F sub U times ANV. Okay, now limit states under concentrated forces. So when we have concentrated forces, we have to look carefully at how the load is applied and how is it transferred, and if there are any limits associated with it. The first limit state is web crippling. So the web crippling limit state is given in equation J10-4, J10-5A and B, and that depends on the location of the concentrated load from the end of the member, whether it's applied at the distance greater than D over 2. D is the depth of the member, or less than D over 2. And you can see in the image how web crippling, may happen. And it depends on the web thickness. It depends on the depth of the member. It depends on the thickness of the web, thickness of the flange, modulus of elasticity, yield strength of the web. And also it depends on L sub B, which is the bearing length of the concentrated load. And we have, so here you can, look at that's L sub B. That's the for example, if it's a column supported by a base plate, how the load, what is LB? And if it's within the beam, how the load is distributed from the point of application throughout the member. Or if it's a reaction, the reaction is also concentrated load. So you can see how LB is and how it's, its effect, within the member. And sometimes for design, so the capacities are shown in equation J10-2 and J10-3, whether it's within the member or whether it's at the end of the member. And sometimes, the bearing length is a design parameter that we have to calculate. So we calculate that using the equation shown. That's the capacity divided by F sub y times the web thickness is 2.5 K, and K is shown here. That's the fillet distance, as you can see here, and also at the top left, that's the K distance of the top flange and at the bottom flange. And if it's a standard shape, you can get that from table 1.1 of the AISC manual. The other limit state is web sideway buckling. Again, due to a concentrated load. So the webs typically are slender, many cases, especially for deep members, they are slender members, and they may buckle about their weak axis. So if you have a concentrated load, that's a possibility. So they are checked using equation J10-6 and J10-7, and they depend on the depth of the member between the flanges, the web thickness, the flange thickness, and the bearing length, and the C sub R factor, which is given below for different cases. And flange local bending limit state, that's as you can see here, the flange bending, and this in these cases, this will happen, for example, in moment connections or seismic connections. You will have a bending in the flange, so that's a local bending that we have to of course check if if the part of the flange will bend due to a concentrated load, which is typically a simple check. We have web local buckling limit state, so that's also a possibility. Again, could be in a seismic connections, or could be in just a typical gravity connection when subjected to a concentrated load. And then we also may have flexural yielding, of the web. And here you can see when, those, black areas, during a test, that shows that, we have web local yielding at these locations. And also playing action, when you have, for example, a WT connected like this, and you have an axial load applied to it, so you can see the gap on the deformation of the WT. So that's something also we have to consider, and we have to avoid in our design. Also, we have Whitmore section yielding and buckling of a gusset plate. So when we have a braced connection, for example, you may have tension force, compression force, So here, if you have a compression force like this, so the plate itself may buckle as a result. So we design the brace for buckling, of course, but that force eventually is transferred to the gusset plate. So we have to make sure that the gusset plate doesn't buckle. So here you are given the parameters of how the section is calculated to check if that section will buckle under a compression force. So basically it goes from the first bolt to the last bolt, and then with an angle of 30 degrees to create the effective section in resisting this force. So that's LW. And then we have, of course, the thickness of the gusset plate. So we can check if buckling will happen or not, or we have to design it for the buckling not to happen. And of course, if it's tension, then we have to worry about yielding. Now we look at shear connections that are typically used. So we have all bolted double angle connection, as shown in the figure. So now we will list the different limit states that are applicable for each connection. So we talked about, the calculations of the different limit states. I mean, most of them. And we will talk about the tables that cover the design of these types of connections. And we will talk about what's covered in the tables and what's not covered in the table. This is very important because, many people, they just take the capacities from the table, but the tables do not cover all the limit states. So we have to make sure that we are aware of that, and we check the additional limit states that are not given or covered by the tables. So this type of connection is has limit states that such as bolt shear, block shear, bolt bearing, flexural yielding, local web buckling, shear rupture, shear yielding. We talked about all these limit states and the equation for them. Now, the limit states covered by the tables are bolt shear, bolt bearing, shear yielding of the angles, and shear rupture of the angles. And we have bolt bearing on the beam web. We have also for beams coped at the top only, we have block shear rupture is also considered. And for beams coped at both flanges, we have shear yielding and shear rupture. Okay. Now, flexural yielding and flexural rupture, this is due to the coping of the beam, that's not covered by the tables. Okay, so that needs to be checked independently, and we have a procedure in part 9 of the AISC manual to check a coped section, flexural yielding and flexural rupture. So we need to follow that to check these two limit states. So the tables for the all bolted double angle connection is given in table 10-1. So we have here the number of rows of bolts. So we have 12 bolts. We have also guidance on what beam size this may be applicable. So that's a W44. The angle is based on A36 steel. The beam is based on 50 KSI steel. And then whether the threads are included or excluded, whether we have slip critical class A, fraying surface, or class B. That's for group A, if we have for the group B, and then the hole type, whether it's a standard bolt hole or if it's oversized, short slotted, etc. And then the angle thickness, whether it's a 1/4 inch angle, 5/16, 3/8, and 1/2, and the capacity in ASD and LRFD for the 12 bolted connections, considering the limit states that are covered by the table that we just talked about. Okay. So basically, you will get most of the limit states from this table covered. You just need to check one or two. And if, for example, the flexural yielding, flexural rupture, if it's uncoped, then maybe you don't have to worry about it. Everything will be covered by the tables. Okay, so that's the lower part. That's the lower part of the table, which is beam web available strength per inch thickness. So this is for LEV is given in the figure, here. That's this distance, the vertical edge distance. And we have LEH, that's the horizontal edge distance. And we have, if it's coped, a top flange only, both flanges, and if it's uncoped. And also we have one thing here, which is support available strength per inch thickness. So we have a beam supported by another beam. If we go back, for example, here, we have a beam supported by another beam. So we check also the support strength, because we connect, we connect to it, and that's in kip per inch here. So you multiply this value by the web thickness of the support to get the capacity. Yeah. So many things are covered in this table. Now the double angle connections may be, also bolted welded. Instead of all bolted, could be bolted welded, as you can see in the figure. So in this limit state, we have, in this connection, the limit states that we need to consider are block shear rupture, bolt bearing, bolt shear, flexural yielding, local web buckling, shear rupture, shear yielding, and weld strength. And what's covered by the limit state, what's covered by the table, is all the limits, all the bolt-related limit states covered in table 1 are also covered in table 2. Table 2, table 10-2 allows substitution of the welds for the bolts. So we have also the weld shear need to be checked, and we have also shear rupture that we need to check. The capacities are based on E70 electrodes. So this is table 10-2, available weld strength of bolted welded double angle connections. Okay. Again, this depends on the, again, N is the number of bolts, L is the length of the connection, and then we have the weld size also. And whether we have weld A or weld B, it depends which side of the connection you are welding. Okay, so so you may weld the two angles to the web, or you may bolt the two angles to the other web. So you have case 1 and case 2, as you can see in the figure. And then we have also the all welded double angle connection. So as you can see, if it's all welded, then we have much less limit states need to be, checked. So you have shear yielding, shear rupture, and weld shear. So again, when we have bolts, we have, from a design, point of view, we have a lot more calculations that we need to do. Okay, what's covered by the tables is weld shear and shear rupture. Again, these are based on E70 electrodes. And here, table 10-3, the AISC manual, that's part 10. So we have the capacities for all welded double angle connection, and they depend on the length of the connection, the weld size, and we have capacities for both weld A and weld B. Now shear connections. This is another common type, which is single plate or shear tab connection. So we have just a plate that's welded to the support and bolted to the supported member, the beam. So the limit states here, we have bolt shear, we have bolt bearing on the web, shear yielding of the web, and for the plate, we have bolt bearing, shear yielding, shear rupture, block shear, buckling, flexural yielding with shear interaction, and we have also the weld shear because it's welded to the support. Okay, this is a simple, easy connection, but we have there are many limit states that need to be checked, and this is the detail of it given in the figure 10-11 of the AISC manual. Again, the weld is based on E70 electrode. So what's covered by the table is bolt bearing on the plate, shear yielding of the plate, shear rupture of the plate, block shear of the plate, and weld shear. So those are covered. Bolt bearing on the beam web, shear yielding of the beam web should be checked independently using the limit states that we discussed before, the equations that we discussed before. Table 10-10A gives the single plate connection capacities that covers the single plate bolts, welds for different plate thicknesses and for different weld sizes, okay, that are given at the bottom of the table. Again, it starts from 12 bolted connection, N equals 12, and for group A or group B, and whether the threads are included or excluded from the shear plane, and the hole type, whether it's a standard hole or short slotted hole. So the plates are, the tables are based on plates that are 36 KSI. Okay, single angle connection. That's another type. We talked about the double angle connection, but this is single angle connection, welded bolted. And here the limit states that need to be covered are bolt shear, bolt bearing, block shear rupture, shear yielding, shear rupture, and weld strength. And what's covered by the table is bolt shear, bolt bearing, block shear rupture, shear yielding, shear rupture, and weld strength. And again, the capacity of the welds is based on E70. This is given in table 10-12, bolted welded single angle connection. This is not commonly used, but I mean, if you are using connection from one side, I mean, many people use just a single plate connection, but you know, this is another option to use. Now, welded-bolted T connection. So here we have a T member that is connected to the beam web and then also connected from both sides of the web to the supporting member. So instead of using double angle connection, you have a T connection. Okay, but you have of course, you have a single shear because you have, you know, the web of the double T is from one side of the beam web. Unlike the double angle connection where you have angles from both sides, you get double shear. So this will have less capacity, but it's an option and it's used for different applications. So the limit states for this connection type is block shear rupture, bolt bearing, bolt shear, flexural rupture, and shear rupture, shear yielding, and weld strength. No tables are available for this type of connection. Now, tables in part 7 of the manual can be used for the bolt limit states, such as bolt shear, bolt bearing, and block shear, and the weld can be calculated manually. So you can use other tables to check the different limit states, but not in one table. And here we have the bolted unstiffened seat connection. So we have the seat connections, that's another type. We have stiffened and unstiffened. We have, you know, bolted, we have welded. So here, as you can see, the seat connection here, you know, everything is supported by the 4 bolts that you see in the figure. So it's the side that's connected to the column or to the supporting member. That's where the capacity. In many cases, you will see an angle like this as a seat, and then you see angle at the top This is typically shown in many of the typical details, but the one at the top does not take any load. That's typically used for erection purposes. But the capacity, the entire reaction need to be designed and supported by this connection, the bottom seat connection. So the limit states covered here are that we have the web crippling, we have local web yielding, we have for the seat angle, we have flexural yielding, we have shear yielding, we have flexural rupture, and we have shear rupture. And for the connectors, we have bolt bearing and bolt shear. So we have to consider all these limit states. And here, that's what when I talked about the top angle. So you can see that. So that's typically smaller size, 2 bolts, just to stabilize the beam during erection. The limit states covered by the table are shear yielding, flexural yielding of the outstanding angle leg, and the bolt limit states, bolt shear, bolt bearing, and block shear. Those are covered by the tables. And table 10-5 gives the capacities for all bolted and stiffened seated connection. And that depends on the required bearing length of the beam, the outstanding for the the outstanding leg, and then you have the angle thickness given, and then you have the angle length, which is 6 inches, common for all, and based on that you can determine the capacity of the unstiffened seat connection. This is welded and unstiffened seat connection, as you can see. So the supporting part is welded to the column, not bolted. Okay, so here we have flexural rupture, flexural yielding, local web yielding, shear rupture, shear yielding, web crippling, and weld strength are the limit states here. What's covered by the table: shear yielding, shear rupture, and flexural yielding of the outstanding angle leg, and the weld strength. Again, the weld is based on E70 electrodes, and table 10-6 gives the capacity of the welded, all welded and stiffened seat connection. Okay, end plate connection, that's a shear connection. So as you can see in the figure, it's a plate that's bolted to the support, and then the beam, the supported beam, is welded to that plate. So that's an end plate shear connection. So here we have block shear rupture, bolt bearing, bolt shear, shear rupture, and shear yielding and weld shear are the limit states. And what's covered by the table is bolt shear, bolt bearing on end plate, and shear yielding of the end plate, shear rupture of the end plate, block shear rupture of the end plate, and weld shear, and shear rupture of the base metal that's due to welding. So we have table 10-4, that's the bolted, welded shear end plate connection. That gives the capacity based on the bolt type, bolt group type, whether it's a group A, B, or C, and then you have with the thread condition, whether it's N or X or slip critical, and the hole type, whether it's a standard, oversized, or short slotted holes, and the end plate thickness, that's 1/4 inch, 5/16, and 3/8, etc. And here we have the weld and beam web available strength given at the bottom part of the table, and also the support available strength in kip per inch, similar to table 10-1 that we discussed before. So that's given here also for the shear end plate connection. So that's for shear connections. The tables, the provisions, the common types, that are used. So then the connection limit states that that we need to consider in designing, you know, these connections. Now, for moment connections, so it depends on the type of the moment connection that we're using, whether it's a bolted flange plates moment connection, or whether it's a welded flange plates moment connection, or if it's the flanges, if they are welded directly to the support. And that's what determines the limit states that need to be checked. So in moment connections, there are no tables, but I mean, for these types of connections, we covered the limit states that need to be checked. So here, what you will have, you will have forces applied at the connection, axial forces, of course, applied at the connection at the top and the bottom once you resolve the moment. And then you take that force and then you check, for example, bolt shear, you check bolt bearing, you check shear yielding, you check shear rupture, all applicable limit states. So block shear rupture for the plates and for the beam flange, that's a limit state we need to consider. Bolt bearing in the plate and on the beam flange, bolt shear, and the plate buckling, because you will have typically, when you resolve the moment, you will have a tension force and a compression force, and you have tension rupture on the plate and on the beam flange, tension yielding on the plate and the beam flange, and you have also the weld strength. So you have an axial force, and then you have a weld that is perpendicular to it at 90 degrees. So we can take advantage of that angle there. And in some cases, it's parallel, as we will see, and the all bolted double angle connection. So here you have, in this case, we have, it's welded, as you can see. So we have less limit states need to be covered: plate buckling, tension rupture, tension yielding, and weld strength. Okay, that's a welded flange plate moment connection. And this is the directly welded flanges. So you may have directly welded flanges to the support. It could be, any type of, like partial joint penetration weld or complete joint penetration weld. So the limit states we need to consider: compression buckling of the column web. We have the local flange bending. We have local web yielding, and we have the weld strength as well. In the moment connections, we have also the splice connections, all bolted splice connections. So we have plates at the top and bottom for the splice, and we have also a shear plate for the shear between the two parts of the beam that are joined together. So in this, we have to check block shear rupture, bolt bearing, bolt shear, flexural rupture, flexural yielding, shear rupture, plates and flanges, shear yielding, plates and flanges, tension rupture, plates and flanges, and tension yielding, plates and flanges. Everything need to be checked to make sure that the load can be transferred from one end to another. Column splices, that's another type of connections. And of course, this will happen in every project and multi-story buildings. So we have bolted connections, we have welded column splice connections. And the limit states that are covered here are bolt bearing, shear, bolt shear, shear rupture, shear yielding, tension rupture, tension yielding, and weld strength. And we also have column base plates. So the base plates could be supported, the column base plates could be connecting a column to a steel member, as you can see on the right figure, where we may need a stiffener to take all the load from the column that's supported by that beam. And so the base plate has to be designed to connect the base plate to the beam flange, or base plate connected to a concrete foundation. So the base plate can be designed, of course, using AISC design guide number 1. That talks about, gives a complete procedure of designing the base plates and also the concrete and the anchorage to concrete. So the limit states for column-based plates, since they are bolted, bolt bearing, bolt shear, and bolt tension, flexural yielding plate and the connection elements, and the weld strength. So typically the column is welded to the plate and the plate is bolted either to another member or to the concrete foundation. So that's on the in the design and the limit states. Now we will go and some practical considerations for connection design. So these tips are suggestions. And there are always several good solutions, and they go on a case by case, but these are general cases that you may consider in your design, and they also are based on constructability and contractor preferences. Constructability. So considering constructability, when you design the connection, you put the members together with a connection. So try to make it as simple as possible. So the constructability is equals to economy. So the simpler the connection, the less material you use, so the cheaper it is, and the less labor it is. Again, which is the same thing, simplicity is economy. Least weight does not always mean least cost, because there is labor also involved. Fewer pieces, that's a greater economy, and efficient connection design, that's a reduced cost. Show the reactions. Now this is very important. Show reactions. Now this is strongly recommended. If it's not a must, in my opinion. If you are designing the connections, you need to start from, of course, you need the loads. So it's very easy to show the connections on your beams, and the connection designer will design for the actual reaction rather than full capacity or the percentage of the capacity of the member. And there are so many variations where you may have concentrated loads, and as we will see, and things may not be right. So show the reactions, especially now with the computer programs. They can show reactions on all beams, and you can show that in your drawings, especially if it's of course a delegated design, or if it's a design within the same office. So if the fabricators are doing that, so they will have the reactions, they know where to start. Do not require connections to be designed for full capacity, as I mentioned. Avoid notes such as in your drawings, such as connection shall be designed to support full shear strength of the member. Do not require connection strength to be based on the reactions of table 36 maximum uniform loads. This is, of course, very common, and it shouldn't be like that. You will end up with way over designed connections. And avoid notes such as connection shall be designed to support reactions occurring from uniform loads equal to 150% of the uniform load capacity. Again, from table 3-6 of the AISC manual. show the reaction. So here, this is an example of where you have distributed load. You have a reaction on one side, 54 kips. You have a reaction on the other side, 234 kips, which can be, it can be missed easily if you have a concentrated load. You just talked about this. The effect of concentrated loads on the beams may not be shown on table 3.6 of the AISC manual. Provide moments and axial loads. Also moments, that's another thing that I have seen and I always, requested. Whenever I design connections, for fabricators, I ask them to go back to the structural engineers and provide moments so we can design for, actual loads. Axial loads in hangers, drag struts, braced frames, truss members show the axial loads there and do not require connection to develop the full capacity of the section. That may lead to way over designed connections. Provide load combinations and directions of reactions, forces and moments. Of course, if you have both directions, it's both directions in the case of, for example, seismic. But if it's one direction, just provide the direction. Also provide the forces and provide the moments. Require connections to be designed per the requirement of the building code, AISC 360. If for gravity connections or for connections for systems with or response modification factor equals to 3 or less. And if you have a seismic steel system where R is greater than 3, like 3.5 and 3.25 and more, you have to consider the AISC seismic provisions, AISC 341. Allow use of bearing bolt strength values were permitted by the building code. Avoid notes such as all bolted connections shall be designed as slip critical connections. I mean, there's no need for that. Use, bearing type connections, slip critical connections. They are used for, certain applications. Permit the use of one-sided connections. There used to be notes on drawings, avoid one-sided connection if possible, and do not use for beams deeper than 18 inches, etc. So we can allow using one-sided connections, like single angle connections, single plate connections. You can do that easily with those types of connections. Permit the use of any size and type of bolt. Don't restrict the bolt diameter or to 3/4 of an inch, as used to be in many in practice. You can use 7/8. You can use 1 inch if needed, and you can use less bolts if it's larger diameter, maybe less bolts. And of course, that's another issue. If you restrict it to 3/4 of an inch, and then you end up with large number of bolts, you may have an issue of not being able to fit these in the connection. So give yourself some flexibility on that. Permit the use of short-slotted holes in shear connections. They don't have to be standard. So don't restrict it to standard hole sizes. Delegate connection design to the fabricators. So, I mean, this is typically the practice. In most of the U.S., maybe except California, where connections are designed by structural engineers and shown on drawings, but the connections can be delegated to the fabricator, and they will do the design. So if you do that, that has to be done properly. So you need to provide all information related to connection design, such as reactions and what are they based on, LRFD load combinations or ASD load combinations, anything related to the loads, and anything that you think as a structural engineer the fabricator should know about connection design, because they know connection design very well, but they need to know about your structure and the connections that you want them to design. You should provide them with that. Now, is a possible note for delegating connection design when R equals 3. Structural steel connection shall be designed in accordance with the requirements of the building code and with AISC 360, using connection design procedure documented in the publications such as the AISC Engineering Journal, the AISC Steel Construction Manual, and the AISC Steel Construction Manual Design Examples. That's, R equal 3, you don't have to worry about seismic. So everything can be done with AISC 360. Frame girders to column flanges and beams to webs. So girders typically are larger in size and the flanges may be wider. So frame those to the column flanges. Beams have typically less loads. They are smaller. They have a smaller beam width, flange width. So you can fit those probably into the column. So try to do that. Size columns to eliminate need for stiffeners. So again, the less pieces you have, the better, the cheaper, the cleaner for your structure. So if you increase the column size, having larger column sizes will not increase the cost by much. It's not significant at all, changing column sizes. But having too many pieces like stiffeners and welding and that you may use for connection design may cost will end up with high cost. So consider sizing the columns higher to avoid using stiffeners in at the connections. Where column stiffeners cannot be avoided, make opposing beams the same depth to avoid something like this. Okay, so you can use both beams same depth, even if you don't need that for connection purposes. You can do that. Use the deepest practical column. Avoid W8 columns. It's hard to fit a connection in a W8 columns. So here you can see that W8s. What is the T distance that remains? 6 1/8, and look at the connection. How it's very tight. Where if you have a W10, it's a little bit bigger. W12, it's bigger, and W14, it's even bigger and better. Orient columns to minimize skewed connections. So skewed connections are difficult and they are expensive. So look at the column orientation to have straight members and straight connections, square connections. Orient columns in braced frames square. So it's a braced frame. There's no need to, even if the geometry of the building requires something like that, but there's no need. So you can just change the orientation and it doesn't affect here. The braced frames doesn't really make a difference in terms of resistance. So, but for the connections, it makes it complicated. Orient columns in braced frames square to the beams and braces. So here you can see if we have the connection is to a flange, it's much easier than if it's to the web, as we will see. The gusset plate size will be less, the connection will be easier, and the geometry of the connection, for its design will be a lot easier. And frame members with very large reaction square to columns are preferable to the flanges. So if you have large reactions, you can see, look at the size of the connections here. So, and the possibilities, if you are if you are framing to a square column to the flange, you can see to the left how clean the connection is, versus to a skewed column to the flange, how complicated the connection will be with 2 rows of bolts. And if you are connecting to the web, on the third figure to the right, you can see how complicated the connection would be and what's the number of bolts that is needed there. Configure framing so that no more than 1 beam frames to any one side of the column. So in a plan, it's just a line, and you could do something like that. But when you detail the connection, you have flanges and you have the flange width. This will of course complicate the connection at that location. You can see that. So you can see when you have the 2 members coming, where you have to cut, you have flange interferences where you have to cut flanges, and this will of course, this is an additional cost, and since you have removed the flange, you have to reinforce the web to substitute for that, so that add to the cost. And head off steeply skewed connections, again, you can when you have steeply skewed connections like the ones on the left, how can you avoid that? So the member doesn't have to frame into for example, a beam into a girder, to the girder itself. So you can have an additional beam to support that beam, as shown in the figure to the right. Configure framing to minimize skewed connections. So here you have 2 examples where how you may do the framing and you end up with many skewed connections, versus if you configure the framing and you minimize the number of skewed connections. I mean, sometimes we have no choice, but we can look at that carefully and configure it to minimize the number of skewed connections. Favor pipe columns over square, rectangular HSS connections. So in square configurations, you may end up with skewed connections. But if you have a round HSS column or a pipe, we don't have that issue. So you can consider that. Watch out for connection interferences where beams are slightly offset at the columns. So again, in drawings, in plans, you will see something similar to what's on the right-hand side. For detailing, when you detail it, you will see the interferences between the flanges and the column. So we need to look at that carefully, so we can locate the beam that's offset at the right location. Beams with flange bolted moment connections must have sufficiently wide flanges to install bolts. So we need to be careful about using sections that have small wide flanges, such as 4-inch flange width, or 5-inch flange width, or even sometimes 6-inch flange width may not be appropriate for these types of connections. And provide sufficient information on the drawings to minimize uncertainty among bidders. So the more information you give on the drawings, the more clear, the requirements about your design will be, the more accurate the bid will be, and you will avoid many RFIs and many issues, during the project. Do not delegate design of plate girder welds. So if you are designing a plate girder, just do the complete design yourself. There's 3 plates connected together, where you have slender web flanges. There's a procedure for that in chapter F of the AISC manual. You can design the plate girder completely with the welds, and of course you can use fillet welds. There's no need for complete joint penetration welds for the plate design of the plate girders. Think about how the connection will be detailed when you have delegated design and you have something like a double plate girder like this. So how the connection will be done. So think about how these members will be put together with other members when you design it, not only just sizing the members. And configure HSS framing to simplify connections. So sometimes this may complicate. If you have HSS members, the connections may be complicated. Here, where you need to cut the HSS versus if you configure the framing to avoid that, and whether you want to weld to the wall of the HSS or you want to use through plate. So look at the options. If you can avoid any cutting through the HSS or on the HSS for coping purposes, you can avoid that easily by just configuring the connections. Some welding tips. Strive for downhand or vertical welds. Avoid specifying all-around welds. This happens a lot, so avoid doing that. There's no need for that. If you need that for strength, there's no problem. But if you don't need that, you don't have to allow all-around welds. Avoid specifying CJP, complete joint penetration welds, at moment connection. Again, there's no need for that. That's why when we talked before, provide the forces, ask for, provide the moment at the moment connections, and if you are designing the connection for a structural engineer, ask for the moments. And favor fillet welds over groove welds. It's cheaper and it's easier. Select efficient diagonal braces, single angles, that's good for small loads, double angles, efficient connections, double shear connections, that's important, of course. And then HSS, the highest brace strength per pound of steel. Field welding required for installation. So HSS, they are great for braced frames. They require field welding. And we cannot use bolted connections. Of course it's possible, but it will not be a simple connection. W shapes, good for high axial loads, but the connections are not simple if you are using shape for diagonal braces. So here you have some examples for single angle or double angle, for HSS brace, and for a wide flange brace. Configure slopes for diagonal braces, 35 to 55 degrees, so you can see why. So when you have, for example, on the figure to the left, so you will have a small angle, for the brace. The brace will not be that efficient. That's number one. And of course, it will affect the connection at both ends. Versus if you use, the configuration on the right, you will have a better angle for the brace. The brace will be more efficient in resisting the load, and the connections will be easier. So here here's what this may look like in terms of the angle and the size. It will affect the size of the gusset plate if the angle is not sufficient. So you can change the configuration, and you will end up with more efficient brace in resisting the load and simpler connections. Orient columns in moment frames for strong axis bending. So this is something that for more resistance for the deflection. And sometimes, of course, at certain areas we have to have it in the weak axis, but you don't have to have a moment connection there because it will not be that efficient. So you can have a simple connection on one side and you have a moment connection on the strong side. And this is an example of these moment connections that are made to the flanges. They are efficient, they are simple to do, versus when you have a beam to column connection, it's to the web, where you have to have coping. You may need stiffeners, and of course the material will be more, and the labor will be more. Run heavy moment connection connected girders through columns to simplify flow of the moments through the columns. So if you can do something like this, that's a possibility. So you can compare here the moment connections and the number of bolts used in these two types of connections. So if you can run the column through, it will be a lot simpler, the connection, and of course the labor will be less, and it's more efficient. And run cantilever roof beams over the top of the columns. So stop the column and run the beam over, versus if you do it, if you run the column all the way to the top and connect it with top and bottom plates, like the figure on the right, there's a lot more labor and a lot more material in that one than the one in the left. Minimize gingerbread. The gingerbread is little pieces of steel. So brace angles, relieving angles, bend plates, stiffeners, web doubler plates, and little beams. Try to minimize all these small pieces of steel. Avoid skewed beam to column moment connection. I mean, this is it's a moment connection that's very difficult to detail. Avoid full depth stiffeners where possible. So you may need stiffeners to transfer the load, so you don't have to extend the stiffeners all the way to the bottom flange. That will require, of course, more details and cutting the plates and fitting them to the bottom flange and welding them. So there's no need for that. Try to avoid doing that. And simplify base plates and anchor rod details. By looking at the configuration of the fuel base plate and the column location in it. So this could be simple, unless, of course, sometimes some columns and base plates are supported on top of walls. There is no way to have the configuration that you want. So in that case, there's no choice. But if you can, you can have a simpler and regular configuration of the base plates and the anchors. Some constructability tips for hangers: avoid pipe hangers. If you can, and omit stiffeners that are extended into members. And if you can have just a plate, basically a plate connection or a plate member or an angle member with the simple connection without stiffeners, like the ones on the right, that would be easier to build and with less pieces for the connection. Understand fabricator preferences regarding preferred connection details, like shear connection, moment connections, brace connections, and truss connections. See, the fabricators, they are a lot more knowledgeable about connection design and putting steel members together than engineers in general. So understand their preferences also, because they will provide the material. So it's good to understand their preferences and have a talk about it. So that's all I have. Thank you for listening. I'll be more than happy to answer any questions. Do we have any questions? Please send questions to chat or Q&A if you have any. You have my emails. Feel free to email me if you have any question as well. Okay, if there are no questions, thank you very much for listening. Again, my email is there. I'll be more than happy to answer any question if you have when you go over the material. Thank you.